Let's continue our discussion of VSEPR theory and molecular shapes and move from the electron center shapes to the molecular shapes, and let's also predict the polarity of the molecules that result. In the short introduction to VSEPR theory, electron center repulsion and three-dimensional positioning around atoms, we looked at three possible positions of electron clusters or centers around a central nucleus. When there are two electron clusters, as here, they repel each other so that the electrons are positioned 180 degrees from each other. If they get any closer, they'll start to repel. When there are three electron clusters, they repel each other so that the electrons are positioned at 120 degree angles around the nucleus of the central atom. When there are four electron clusters, they get into a three-dimensional situation and position themselves at minimum energy around the apexes of a tetrahedron. The central nucleus is in the center of the tetrahedron. That tells us where the electron pairs will be. Now, where will the atoms be, the ones that surround the central atom? Well, that depends on how many electron pairs are bonding pairs and how many are non-bonding pairs. A bonding pair, as here, will have another atom attached. A non-bonding pair will not. We're going to examine only the most common situations and leave the complex stuff like ions and radicals for discussion and further study. Remember, we want to minimize energies. As a beginning, consider hydrogen fluoride that has one bond center and a very electronegative element, fluorine, pulling against little hydrogen. This is a linear molecule that is very polar, electronegative on one side, non on the other, a very polar molecule. The fluorine is pulling the bonding pair so hard that it spends most of its time there and little time there. Hydrogen fluoride is linear, but it's lopsided or polar. By contrast, the element fluorine, F2, is linear and nonpolar. It is not lopsided because each fluorine pulls electrons equally. Fluorine, the element, and all the other halogen elements are nonpolar. Second, let's look at two electron clusters. Beryllium has two valence electrons, so it can form bonds with two hydrogen atoms. The electron pairs that result will get as far away from each other as they can, so the bond angles are 180 degrees. That means that beryllium dihydride is a linear and nonpolar molecule. Likewise, Lewis structures tell us that carbon dioxide, pictured here, has two electron clusters, both double bonds, and they will be as far away from each other as possible with 180 degree bond angles. Carbon dioxide must be linear as well. Furthermore, any bond polarity or lopsidedness in the carbon dioxide bonds will be offset by the fact that it's linear and each dipole cancels out the other one. So carbon dioxide and similar molecules would be nonpolar. Third, let's examine three electron clusters. Boron has three valence electrons, so it can form bonds with three hydrogen atoms. The electron pairs that result will get as far away from each other as they can, so the bond angles are 120 degrees. That means boron trihydride is flat and triangular. Chemists call this shape trigonal planar. Fourth, let's look at four electron clusters. Carbon has four valence electrons, so it can form bonds with four hydrogen atoms. The electron pairs that result will get as far away from each other as they can, so the bond angles are 109.5 degrees, and the electron pairs in hydrogen atoms are at the apexes of a tetrahedron. That means methane, or carbon tetrahydride, is tetrahedral. I think it's also clear that methane is nonpolar. Any bond polarity is offset by the other three dipoles pulling in the other direction. Let's caution you though. Chloromethane is tetrahedral, as you see, and it is pulling, since the chlorine is pulling the electrons more than the hydrogens, this is lopsided or polar. So chloromethane, although it's tetrahedral, is a polar molecule. The bonds, polarities, do not cancel each other out. Nitrogen has 5 valence electrons, and so the electron configuration is tetrahedral. When it forms ammonia, only 3 of the valence electrons form bonds with hydrogen. 1, 2, 3. That leaves a lone pair, a non-bonding pair on one end of the molecule. So ammonia is a little bit lopsided, with a negative end and a positive end. It is a polar molecule. Most covalently bonded nitrogen compounds have polar parts. Oxygen has 6 valence electrons. When it forms water, only 2 of the valence electrons of oxygen form bonds with hydrogen, here and here. That leaves 2 lone pairs, 2 non-bonding pairs on one end of the molecule. So water is very lopsided, with a negative end and a positive end. It is a polar molecule. Most covalently bonded oxygen compounds have polar parts. Water is the most polar substance you will commonly run into. Only hydrogen fluoride is more polar.